In person. Let's.
Do you mind if we do a short break, like only 5 minutes? That will give you time to, get refreshed, go to the restroom, and come back because we're a little bit behind schedule. I suppose if worse comes to worse, the lecture could just spill over to after lunch, but I'd rather not do that right now. Thanks.
So, why would you want to see one slide?
Yeah.
Because you can.
Because you can. Let me punch it in up real quick. Okay.
Sure. Let's see if that is live.
I never had that happen.
Where did you live? You were in the headquarters show? This is the NATO console. Yeah. This is Air Force Command Lisbon until it checks out. That's it? Yeah. There's no other location? There's another location, but that's here in Lisbon. So 116. Conco, Air Force Relations, and then JELD, which is the Joint Analysis Luxembourg Center. So I don't know what they say what in Portugal? They just said Portugal. And it didn't have any headquarters name or anything. It said NATO, then it said Portugal. It's 12. And so I imagine I'll be talking about once. Well, this is for JF, that's where this is. And this is inside the town called Oeiras, O-E-I-R-A-S. And like this area is like super tourism. Yeah, that's what I've noticed. Everything's like short term rentals. Yeah, and then the other big tourism area is down here in the south. That's where a lot of the tourists are.
Because 13 was in the 12 times.
So generally,
if 13 was 0, it's 5.
generally, people who live on either side of this, but very few people live all the way in the actual traffic. Some people do, but it's not.
This one is mathematical as much as it is.
But a lot of people live
Okay, thank you.
Cash Price in Estoril. There's another smaller town here called Estoril. Right here. There's South Pedro. Estoril.
Did you just link up with the airline when you got there, or were you in contact? Because I'm not finding that in the last couple of days.
There, the way it works for us was, you can work with NATO, but they have a couple that work for them a lot, and they know
They recommend, NATO recommend.
well, those realtors that work with NATO, they know that you have contracts, and what the U.S. contract. And so therefore, they know what landlords are agreeable with that contract. Because we tried to go outside and we found a landlord that had never worked with NATO and didn't want a contract. So we found a place, but we weren't willing to agree with the contract, so we didn't really find a place. And so some people wonder if there's like a little, collusion going on there, but between the realtors and the people that work at the place.
It
basically.
Okay.
So at least they know who gets them. They'll do it
I don't know about
cases.
computer brand, but maybe the last.
Started
I'll talk to you about it.
So thanks, I appreciate it. Short break. I guess I'll a few more seconds. You're good. All right, I'm good. All right. So we've defined modular addition and modular multiplication. You just take the remainder at the end, or you can take remainders as you go, or you can freely substitute conjugate them. As long as what you have, what you get out is good. So we've defined modular addition multiplication. We'd like to extend that to modular subtraction and modular division. So these are inverse operations. So modular subtraction is going to be modular addition of the modular negation. Just like subtraction is the addition of the negation, well, now we're going to define a modular negation. So an additive inverse of A, also called the negation of A, in mod n, and so in Z sub n, is some number B in Z sub n such as A plus B is equal to 0. So for example, mod 6, 2 plus 4 is equal to 0. Right? In modular addition, mod 6, 2 plus 4 is equal to 0. So 2 and 4 are additive inverses of each other. Likewise, a multiplicative inverse of A is going to be a number that if you multiply it by A, mod n, you get 1. So that's called a multiplicative inverse, or a modular reciprocal of A. So if B is an inverse of A, either additive or multiplicative, then vice versa. A is an inverse of B, so they come in pairs as usual. If A has an inverse of either type, then it has to be unique. So we're going to write the modular inverse of 2, mod 6, this way. So we take minus 2, it's going to be like negative 2, but we put a subscript 6 on the minus sign. This is equal to 4. This is the unique number in Z sub 6, that when you add it to 2, mod 6, you get 0. Likewise, the modular negation of 4, mod 6, is equal to 2. So they're inverses of each other. So the modular negation, the additive inverse, we denote like this. For the multiplicative inverse, if one exists, this is terrible notation, I'll admit, but here's how we're going to write it. We're going to write it to a to the minus 1, but we'll put a subscript n on the exponent sign. So this is the modular multiplicative inverse of A, modulo n, modular reciprocal. And it may or may not exist. If it does exist, it's unique, though. All right. So, now we're going to skip all that. Okay. Let me just tell you, one of these is easy to find. Well, zero is its own modular negation. If I add 0 and 0, I just get 0. That's always true. So if A is different from 0, then this is always equal to n minus A. So A here is going from 1 to n minus 1. If A is non-zero, remember A is in Z sub n. If A is non-zero, then it's between 1 and n minus 1. Well, just take n minus A. This is This is also between 1 and n minus 1. So this number is also in z sub n. And when I add a and n minus a in real life, I get n. But then I take the remainder, I get 0. So a plus n minus a is equal to 0. Mod n. So that means that this has to be minus a. All right. So if we have a table, for example, mod 5, if this is a, and this is minus mod 5a, that's always 0, and now I count down from 5. So it'll be 4, 3, 2, 1, like this. All these numbers here are in Z5. So everything's going to be in Z5. Everything in the world is confined to Z5 here. Now, modular reciprocals. We'll skip all of this. Skip that. Here's the thing. Well, I'm going to skip that as well. A in Z sub n, I told you that not all numbers in Z sub n have modular reciprocals. A in Z sub n has a multiplicative inverse in Z sub n, if and only if it's co-prime with n. In English? You can take a reciprocal if you don't have any common factors with n, and vice versa. Okay. So for each a in z sub, let's take z sub 10. Let's try z sub 10. For each a in z sub 10, find its multiplicative inverse if possible. This will be true exactly when a is co-prime with 10. So a has no common factors with 10. Now we already went over what those numbers are. What are they? Less than 10. 1, 3, 7, and 9. There are 4 of them. No, I don't need to write this on the board because it's on the slide. So GCD of A and 10 is 1 if A is 1, 3, 7, or 9. Notice there are 4 of these, exactly 4 of these, and phi of 10 is 4, because phi of 10, that's the Euler-Toschen function, it counts these numbers. So phi of n counts the number of elements of Z sub n that have reciprocals. So there are only 4 elements with multiplicative inverse. Well, 1 times 1 is always 1, so 1 is always its own multiplicative inverse. 9 times 9 is what in real life? It's 81. But when you divide by 10, you get a remainder of 1. So 9 is its own multiplicative inverse in Z10. And then the only 2 that are left are 3 and 7. They got to be inverses. So 3 times 7 is what? 21. Mod 10 is 1. So here's the table of inverses. The inverse of 1 is 1. The inverse of 3 is 7. The inverse of 7 is 3. And the inverse of 9 is 9. So this is the table of inverses mod 10. Questions? All right. Cancellation, let's skip this. Yeah, I can just skip this. I don't think this is that important. And it just takes a long time to slug. So now we can define subtraction and division in Z sub n. So A modular subtract B is just modular addition of the modular negation. So it's the same thing in real life, except you stick these n subscripts over all the operations. Equivalently, you could just subtract b from a in real life, and whatever that is, take its remainder mod n. And that'll give you the same answer. All right. So now a divided by b mod n is going to be a modularly multiplied by the modular reciprocal of b, if it exists. Doesn't always exist. For example, 0 never has a modular reciprocal, right? There's nothing you can multiply by 0 to get 1, modularly or otherwise. So just like in real life, you can never divide by 0. Well, modulo n, there might be other things you can't divide by. So, for example, mod 10, you can't divide by 5. Because 5 is not coprimed with 10, so it doesn't have a modular inverse. And you can't divide by an even number, mod 10, either. You just can't do it. Okay. So the thing is, there might be other numbers besides 0 that you can't divide by. But suppose the modulus is prime. So you have a prime modulus. Then everything in z sub p, so if p is prime, look at z sub p. 0 is not going to have an inverse. But every non-zero element of z sub p is coprimed with p, right? Because p is prime. So in z sub p, you can divide by everything except 0. So you can divide by any non-zero thing. If the modulus is prime, you can do that. So that's kind of nice. So then division kind of resembles more actual division in something like the reals or the rational. For modular theorem, we don't need to cover this because we're going to have a stronger theorem momentarily. We just skip this. And we're going to skip Fermat's test for primality because it's not really that great. All right. So in cryptography, you need to generate large primes, very large. And when I mean very large, I mean thousands of binary digits. So maybe on the order of 10 to the 300 or 400. And these are really huge numbers. How do you test if they're prime? Well, the way you do this is you generate these prime, you generate a random number and test if it's prime. And if it's not prime, you just try again, generate another random number. If you do this a few times, you'll actually stumble on a prime fairly quickly, and that's due to the prime number theorem, which says that the primes have a nice density. They're fairly dense. So if you just pick numbers at random, eventually you'll find a prime, but how do you know you found one when you get it? There are primality tests that work for very large numbers with high probability. So that the chance there's an error. They might give you the wrong answer, but if you run the test several times, and every single time it says that this number is prime, this number is prime, this number is prime, that's very good evidence that the number is actually prime. So the chances, every time you run the test, the chances that the test is wrong, that it says it's prime when it's really not prime, is less than 50-50. So if you run it 100 times independently, the chances that it's going to be wrong every single time is tiny. Eventually, if it says it's prime every single time, then that's very good evidence that it's prime. And there are two tests that do this, the Solovay-Strassen test and the Miller-Rabin test, which we won't talk about. The Miller-Rabin test is used for generating keys in the RSA cryptosystem, which we'll talk about a little bit, but not right now. I'm going to skip over that. So next up is Euler's theorem. Here's where I promise we'll use the Euler-Toschen function. So Patterson was asking the eternal question of why. Here is one reason why. So suppose A and N are coprime, and N is bigger than 0. Let's see. So N here is the modulus. Think of N as being the modulus. and A is being something that's co-prime with M. Maybe it's in C sub A, but it doesn't matter. Euler's theorem says this. If you take A to the power of phi of n, this is the quotient function, you will always get 1 modulo A. This is always true. So this is where it's going to be useful. In particular, if you know what phi of n is, this is a way to get the modular inverse of A. Because the modular inverse of A, you just take this to the phi of n minus 1. Because now if you take this number and multiply it by A again, you're going to get A to the phi of n, which is equivalent to 1. So this is, in fact, this is a way to get the inverse of A, the modular inverse of A. One way. It's not the fastest way necessarily, but it's a good way, and this will work reasonably well. So you can get the inverse by just taking an exponentiation. And A has to be co-prime with n. So the inverse has to exist, and this is the way to get it. It has another application. If A is well, this is just A to the 0, right? Essentially what that means is that anytime you have a phi of n, an additive phi of n in the exponent, you can replace it with 0. So this says, actually, if you're computing if you have a big exponent here, and the base is co-prime with the modulus, you can reduce the exponent modulo phi of n to just get the exponent down very quickly. So we'll do an example of that. So let's compute, first of all, let's do the first application. Let's compute 5 inverse modulo 22. So what's the inverse of 5 modulo 22? Euler's theorem says, well, first of all, compute phi of 22. Phi of 22, well, 22 is 2 times 11. That's the prime factorization. So phi of 22, I mean, the exponents are both 1. So this is going to be 2 minus 1 times 11 minus 1. So that's 10. So phi of 22 is 10. So phi of inverse mod 22 is 5 to the 9th. And now we can do our usual tricks and reduce this mod 22. And if we do that, we eventually get 9. So this claim, 9 is a remainder mod 22. So the claim is that 9 is the modular multiplicative inverse of 5. Let's check that. 5 times 9 is 45. Reduced mod 22 is 9. So 5 times 9 is congruent to 1. So 5 modular times 9 is equal to 1. And so that is correct. So we found the modular inverse that way. Questions on that? Okay. Let's do the second application. Is you can reduce, the second application says that you can trade one exponent for another if those exponents are congruent modulo phi of n. Provided the common base there is coprime with n. So let's do this to compute 5 to the 123 mod 22. Well, phi of 22 is this 10. So here's what we're going to do. 5 to the 123, we can reduce 123 mod 10. The base 5 is 5 here. Is 5 coprime with 22? Yes, it is. Because 22 is just 2 times 11. Okay, and 5 is prime. So Euler's theorem applies, and Euler's theorem says you can then reduce the exponent mod 10. Not mod 22, but mod 10. So you can immediately replace 123 up here with 3. Because the remainder is just going to be the ones digit. So 5 to the 123 is 5 cubed, which is 25 times 5, and now the other tricks come in. So 25 is congruent to 3. 3 times 5 is 15. That number is less than 22, so that's the answer. So that was quick. All right. Question on Euler's theorem. Actually, I caught up with myself. I got plenty of time left, so we won't have to spill over. That's good. Do you want to see another example of this? Okay. So I whipped through that. Pick a modulus somewhere, say, between 30 and 70. Give me some random stuff. 60? 61.
Prime.
61, okay. Let me say, let's make it composite. We can make it prime. We're going to do 2 examples. Let's make it composite first of all.
69.
69.
Thank you, Mr. Maturity.
All right. What is the prime factorization of 69?
3 something.
It's open.
Times 23. Actually, that's it. 323.
Yeah, that's it. Okay, so you could do the usual thing.
I don't need you, calculator.
Okay. So what's 5 of 69?
Yep.
So that's to the first. So it's going to be 3 minus 1 times 23 minus 1.
44.
So 2 times 22 is 44. So 5 of 69 is 44.
What?
All right.
What was 5?
What?
Again?
This is the number of things. This is the number of elements of Z sub n that have reciprocals in Z sub n. So this is equal to the number of elements A in Z69, such that A inverse 69 exists.
So that's the number of real numbers, if we do the 0 to 68 thing, that inversely becomes 0. If you add them together, or subtract becomes 0.
No, this is multiplying.
No, multiplying.
Okay.
Multiplying. So there's some number okay. It's the number of elements in Z69 that are co-prime with 69.
Okay.
Okay. But each element is co-prime if and only if it has a reciprocal. So this is counting the co-prime elements. It's also counting the elements that have a reciprocal because that's the same set of elements.
They're co-prime with each other or co-prime with 69?
Co-prime with 69.
Okay.
Yeah. But that's neither here nor there for us. What is here or there is Euler's theorem. The fact that you can take anything co-prime with 69, take it to the power of, in this case, 44, and you'll always get 1, no matter what you start with, as long as it's co-prime with 69. So, give me a number co-prime with 69.
7.
7. Okay. Let's find 7 inverse mod 69 using this approach. So this, by Euler's theorem, this is going to be congruent to 7 to the phi of 69 minus 1.
So it'd be 43? So
Yeah.
43?
So congruent to 7 to the 43. All right. Oh boy. Okay. Sorry, 69. Okay. Well, what's 7 squared at least? 49. All right. That differs from 69 by not too much. So maybe what I'll do is I'll pull out. This is actually equality. Tell me when this is ready to go. I'll throw it out. This is going to be 7 times 7 squared to the power of 21, right? Because 2 times 21 is 42. Plus 1 gets you 42.
You can work all kinds of witchcraft kind of stuff. So you can...
7 squared is 49, which I can reduce mod 69 to be minus 20. So this is congruent mod 69 to, so I'll write it as 7 times 49 to the 21. This is actually how a computer would do it. It would just do this repeated squaring this way. So it wouldn't bother with the other tricks. So 69, I reduce this to minus 20. It's congruent to that. So this is going to be 7 times negative 20 to the 21. I'm taking a negative number to an odd exponent. So I get a minus sign. I get a net minus sign outside. So this is going to be minus 7 times 20 to the 21.
Just make that 20 times 3, or just 3 times 20 to the 7.
What do we do with that 20?
20 times to the 3 times 20 to the 7? 7? Is that right?
20 to the 3. Oh, but those numbers are so big. I want to keep it below 100. Well, 20 is
4 times 5.
4 times 5, yeah. That's good. 4 times 5. Let's try 4 times 5. So this is equal to minus 7 times 4 to the 21 times 5 to the 21. Okay. So where am I? I got to erase something here. In hindsight, this was probably too big a modulus. 4 to the 4th is what? 16. I'm sorry, 4 cubed. 4 cubed is 64, which is very close to 69. That's nice. Let's use that. Okay. So 4 cubed. So 4 to the 21 is 4 cubed to the 7th. And multiplied by 5. Okay, so 4 cubed is 64, which is congruent to negative 5. So this is congruent mod 69. So that's 64. Congruent to minus 7 times minus 5 to the 7 times 5 to the 21. Negative number to an odd exponent. I get a net minus sign, which will cancel that. So this is equal to 7 times 5 to the 7 times 5 to the 21, which is 7 times 5 to the 28.
4 times 7.
Okay. All right. Maybe we can go a little bit above 100. Let's see. So 5 squared is 25 mod 69 out of the
5 cubed.
5 cubed is 125. mod 69. That might be good. So what's 16? What's 69 times 2?
138.
138.
You get 13.
So coming back to 125, that's a minus 13. Okay. So this is congruent. Well, it's equal. That's right. Equal to 7 times 5 cubed. Now this is 5 to the 28. So if I take cubed, I take this to the 9th, that's 5 to the 27th. And so I have to multiply by 5 to get 5 to the 28. So 5 cubed, this is congruent mod 69 to minus 13. So now I get 7 times minus 13 to the 9th times 5. Okay. So minus 13, I can pull a minus sign out. So it gets an odd exponent. So 13 to the 9th. 13 squared. Is what? 169. So
Let's say about 30.
okay, that's not awful. 169 is what? Mod 69. So 69. What's the next one? That's 138. And what's the next one after that?
So 207.
207. So if I take 169 minus 138, what do I get? 31. Yeah, that's pretty awful, but that's what it is. Minus 7 times
Dude, you're the one that sent me
31. Let's write it this way. 169 to the 4th, that gives us 13 to the 8th, times 13 times 5. Okay. So this is congruent minus 69 to minus 7 times 31 to the 4th, times 13 times 5. All right. Yeah, so this is harder than I hoped it would be. That's my own fault because I let you choose it. All right. Maybe you just plug this in somebody's calculator right now and just get it.
It's 10.
There's 10?
Final answer.
Box it. Done.
What is it in real life?
31.
That should be your calculator should be able to handle that. Remember, it's minus.
Yep.
Okay. Anybody?
13. Negative. Oh wow. Negative 420202055.
It was 4, 2, 0,
20
2, 0,
20
2, 0.
55.
Really? That's like that?
Yes.
That's kind of interesting. Okay. Now, take this number. Let's take this number. Let's make it positive for a second. Let's take positive 4, 2, 0, 2, 0, 2, 0, 5, 5. Divided by 69.
Yep.
Standard real division.
You get 88,259.2.
What do I get?
88,259.2.
Okay. The integer part of that, that's the quotient. that will get the quotient. So if you do the actual division and just truncate it to an integer, as long as the numbers are positive, this will actually give you the quotient. Because if you take 69 multiplied by one more than this, you're going to go over. So this is equal to Q.
That's not right.
Yeah, that's not the right number. I figured.
What is it?
6089884.
6089 what?
884.
884.
0.855.
0.855. Okay. That's Q. Now, how do you find the remainder? So the remainder is A minus QD. So here, D is 69. Q is that thing in the millions. So take Q times D. So take that number, multiply it by 69, and then subtract the result from the original. What do you get?
59.
59. Okay. 58. I'll go with 59. Okay. Now, that was, we negated it. So the actual number was the negation of that. Okay. So positive number, this is congruent on 69 to 59. So if I negate both sides, I still get a congruence. So this number is congruent to minus 59.
The remainder would be 2.
Which is 10.
Yeah. Thank you. I'm impressed.
So 10. Make a long story short, 7 minus 1, 69, is equal to 10. Let's check that. 7 times 10 is 70. Mod 69 is 1. Okay. So notice that this was not the best way of doing it. You could have just gone through the multiples of so here's another, for numbers this small, here's a better way of doing it. And this can be refined to an actual efficient computer way of doing it. Let's do another example. Let's take maybe, how about 11 inverse mod 69? Oh, this might, well, okay. Let's take a smaller modulus.
Cool.
Let's take 26. Let's take 26. 11 and 26 are coprime? All right. So, yeah, take 26 plus 1. That's 27. That's not a multiple of 11. So go to the next.
Find the least common multiple.
Take one more than multiples of 26. Write them all down. So you're going to increment in terms of 26. So the next one is 53, and then the next one is 79, and then the next one is 105. Keep writing that down until you get a multiple of 11. And once you get a multiple of 11, that multiplier is the inverse. So what's the next one after? So none of these are multiples of 11. What's the next one?
131.
131? No.
157.
What is it? 157? That a multiple of 11? No. What's the next one?
193.
193? No. What's the next one?
219.
219? Is that a multiple of 11? It's close. 220 is a multiple of 11. Okay.
I like it.
What's next?
245.
245. Is that a multiple of 11? No. 271. What's the next one? 297. Is that a multiple of 11? Are you sure? Oh, yeah. It is.
It's 27.
This is 11
times
times
27.
27. Is equal to 27. And now we know immediately that this is the correct answer because 11 times 27 is this, and we know that this is congruent to 1. We're just stepping through all the things congruent to 1, not 27, exhaustively. So if the modulus is not too big, this is probably the fastest way to do it. Okay. But I said there are ways you can actually zero in on the correct place more efficiently, and I describe a couple in the book. All right. Let's stick with 26 as the modulus and compute 11. Let's maybe go to 25. I'm sorry. Let's take 11 to the power of 390 on 25. Let's do that. So this is the second use of Euler's theorem. So 11 and 25 are coprime. What is 525? Well, 25 is 5 squared. So this is going to be 5 to the 2 minus 1 times 5 minus 1. That's the formula. So go back to that slide with the formula. That's what you plug in. So this is what? 4 times 4? I'm sorry, 5 times 4. 5 times 4, that is 20. Okay? So if we start with 11,390, and we want to reduce that mod 25, Euler's theorem says that you are allowed to reduce the exponent mod 20. So this will be 390 mod 20. What's 390 mod 20? 10. So this is equal to 11 to the 10th.
That's 1.
Okay. Now let's use our usual tricks. So 11 to the 10th, you could write that as, say, 11 squared to the 5th. What's 11 squared? 121. So this is 11 squared to the 5th. So this is 121 to the 5th. Now, reducing this mod 25, what can I get? What's a good number to reduce this to?
11. And then 11 squared?
Well, 25, negative 4.
Oh.
Because 25, 50, 75, 100, 125, come back 4.
Yeah.
So this is congruent mod 25 to negative 4 to the 5th. Negative 4 to the 5th is, well, that's going to be negative 4 to the 5th, so I can take out the minus sign there. Okay? And that's 2 to the 10th. Right? Which is 2 to the 5th times 2 to the 5th. Or 2 to the 5th squared. What's 2 to the 5th? 32. I'm going off camera, so let me go.
Do we lose the negative after better?
Oh, we probably did, yes. Negative. So this is negative 32 squared. So reduce mod 26, mod 25 rather. 7. So this negative 7 squared, which is equal to minus 49, which is equal to
Wait, pause that for a minute.
mod 25.
No, just because
It's 1. Because you take 0, minus 25, minus 50, come back 1, positive 1, to minus 49. So this is in the range. This is in Z25. So that's the answer. So this is equal to 11 to the 390. All right. All right, I got just a couple more slides to go through, okay, and then we're done. Chinese remainder theorem. So I'm going to restrict it. So the Chinese remainder theorem has a general version. I'm going to restrict our attention to a simple case where I just have two different moduli. So suppose I have two numbers m and n that are both positive and assume they're coprime, so they don't have any factors in common. Think of these are two different. So think of m and n as both being a modulus. So now I have two different moduluses. Then for any a in z sub m and any b in z sub n, there's a unique x in z sub m times n that's congruent to a mod the first modulus and congruent to b modulo the second modulus. In other words, you can find a unique solution to this system of two equations. The first equation says, well, I'll write it. You can write it in this form. X is congruent mod m to a, and x is congruent mod n to b. So you can simultaneously find, for a single value x, you can simultaneously find one that's congruent to a mod the first modulus and congruent to b mod the second modulus. So it's kind of a little strange. But this turns out to be very useful fact. The way you find, and here, 0 is going to be less than or equal to x less than m times n. In other words, x is in z sub m. And this x is unique. You get a unique answer. There are actually lots of x's, but there's only one unique x in this. All the other solutions are going to be congruent to x modulo m times n. So there's only going to be one of them in z sub m times n. All right. So this is what the Chinese remainder theorem says. And the general Chinese remainder theorem is the same, except that I can have more than two moduli. I can have any number of moduli. And they all are coprime with each other. So take any two numbers, they're coprime. You can find and take any residues you want for each of the moduli, and you can find a single x that will satisfy all of them simultaneously, and that x is unique. But this is just a case where I have two numbers. All right. So it's actually easy to write down an expression for x. in terms of A, B, and M and N. And here it is. Let's unpack this, shall we? M times B times, that's hard to read, but that's the inverse of M modulo N. So take M, take its inverse modulo N. And now do the same. The next term is N times A times the inverse, the reciprocal of N modulo M. So these two terms are the same except that you swap M and N everywhere. Okay. And if one of these is not in the a remainder of the other, just reduce M and N before you take the reciprocal. Add those two things together, take the remainder modulo M times N, that gives you that. Okay, just by magic. All right. Here is a check for why that works, but I won't bother with that. Let's do an example. Why is the solution unique? We don't care about that. Let's do an example. Here's the general remainder theorem, general Chinese remainder theorem. We don't care about that. Let's get to an example. There is no example. Here's an example. Okay. So, let's take two different moduli, modulo 2 and modulo 5. Okay. Let's just take two numbers, 3 and 10, and can we find an x that's simultaneously congruent to both of those? And the answer is sure, because what would it be? And it's got to be in z sub 10, because 2 times 5 is 10. So some number between 0 and 9 satisfies both of these. Well, what's congruent to 10? Well, mod 5. 0, 5, 10. But we've got to stick in z sub 10, so it's either 0 or 5. So to satisfy the second equation, it can only be 0 or 5. So how do you satisfy the first equation? Well, mod 2, what are the things congruent to 3 mod 2? They are just the odd numbers. So that first equation is equivalent to saying that x is odd. So this one says that x is odd. This one says that x is either 0, 5, or 10, or 15. It's congruent to 10 mod 5. So there's only one possible answer in Z10 that satisfies both of those. It's going to be, what? 5. Okay. So 5 satisfies both. All right. I think this is my last slide. Yeah. So let's, I got a minute left. Let's do another example. Let's pick two. Give me two coprime numbers, not too big. Say less than 20. 9 and 13. Okay. So give me something in Z9. Give me something in Z13. 7? I heard 7. Let's find an x. And 9 times 13 is what? It's 1. X is going to be in 117, which this is 9 times 13. Find an x now. I'll let you work on that for a minute. You could use the formula, but in this case, the numbers are small enough that trial and error good educated guess is probably the best thing. Anybody get it? I'll give you another 30 seconds.
I'm gonna get it.
Can't get it.
I'm gonna get it.
You're gonna get it.
Feel it.
Patterson's gonna get it. It's kind of like bingo. Give out numbers and. All right. Okay. So no one's gotten it. All right. Here's what you can do.
I got it.
85. Let's check. You divide 85 by 9. 9, what's the multiple of 9 that's close to 85 and less than? It's 81. 9 times 9 is 81. Okay, plus 4, that gives you 85. Okay? So good. X equals 85. That's looking good. What about the next one? 13 into 85. Well, 13 times 5 is 65. So 13 times 6 is 78. Yeah, plus 7 is 85. All right, Captain Gruen saves the day. So how did you do that?
I made a list of 4 plus 9, and then just kept adding 9, and then made another list of 7 plus 13, and kept adding 13.
Good.
There's
When you saw a match on the two lists. Good. That was just what I was going to suggest. So here's how he did it. He writes down. You might start with 4 for the first equation, and then keep adding 9, and now you're getting all the things that are congruent to 4 mod 9. So next is going to be 13, 22, 31, and so forth. You write that list down, and now you write a second list. Do the same thing, but congruent to 7 mod 13. So you might start with 7. Add 13 to that, you get 20, 33, keep 46, 59, and so on. You keep writing down these lists until you see a number that appears on both. And so the next one is going to be 72, and then 85, and you run that a little, and then you go back over here, and you kind of keep them going at the same time. So you add 9 to that, you get 40, 49, 58, 67, 76, 85. That's probably the fastest by hand method for numbers in this range. Numbers that are small. Just make 2 lists. Like I said, there are more systematic methods, and a computer can do this extremely rapidly, even for really large numbers. Okay, solve this. All right, I'm out of time. You're going to learn about public key cryptography when you get to network security. I could do a sidebar. I could do like a little mini lecture this afternoon, describe you how RSA works. It's very easy. If people are interested in doing that, I'd be happy to do that. Okay. All right. So great. I'm a little over. Thanks for your patience. And
Yes, a number larger than that. We couldn't just. I mean, we got to go as far, right?
yeah, for moduli that are really big, you really need to use the formula. And then there are also faster systematic ways of computing modular inverses. So we were doing sort of also like guesswork for doing modular equations. There are much more faster ways of doing it.
Try it out
Okay.
on the WebMonkey survey system.
All right.